In this video, we want to talk about the zeros of polynomial function. Zeros of polynomial function means the x-intercept, means when we set the whole polynomial function equal to 0 and we find x-intercept. But sometimes it's not easy to find the zeros of the polynomial function because the only method that we learned so far for solving polynomial equation is by factoring. And factoring is not always work for our problem. For example, if you look at this polynomial function, if you want to find the 0, you have to set it equal to 0. And if you set the whole equation equal to 0, you need to factor it. We said that every time we have 4 terms, we put them in groups of 2. And then try to find the common factor from each group. If I find the common factor from the first group, which is x cubed, I will get 3x minus 2. Second group doesn't have any common factor. I can only factor 1. And you see that we didn't get the same parenthesis because every time we put the 4 terms in 2 groups of 2 and we start factoring the greatest common factor from each group, we expect to have the same parentheses. If we don't get the same parenthesis, that means we cannot factor that polynomial. We have to use another method to solve that equation. And in this video, we learn about some theorem that can help us to factor polynomial functions and then find the zeros of the polynomial equation. Okay? So the first theorem is called the remainder theorem. The remainder theorem tells us that if you divide two polynomials, if you divide f of x by x minus k, the remainder of that division, that is the same as if you replace the k into the function f. What does it mean? It means if you divide this polynomial by x minus 2, the remainder of this division, that should be the same as replacing 2 into this function. Why I say 2? Because 2 is a number that makes the divisor 0. If you set the divisor equal to 0, you see that x is equal to 2. And if you replace 2 into the function, if you replace all of the x's by 2, let's see what we get. And you know that we always follow the PEMDAS, so we have to find the exponent first, 2 to the 4th power, which is 16, and then we need to multiply 3 by 16, which gives us 48. Find the exponent first, 2 to the 3rd power, multiply 2 by itself 3 times, which is 8, and then multiply 8 by negative 2, which is negative 16. Multiply 5 by 2, which is 10, and then bring down negative 2, and now the last step is addition and subtraction. 48 minus 16 plus 10 minus 2. So 48 minus 16 plus 10 minus 2. And the answer is 40. 40 is the remainder of this division. Now let's see if we get the same answer. I want to use synthetic division and see if we can get the correct answer. So for using synthetic division, we have to set the divisor equal to 0, and we get 2. We put 2 in a box, and then we put the coefficient of this polynomial using for synthetic division. But you have to make sure that there is no missing term when you are dividing. And if you look at the polynomial, start with factor with power 4. So after power 4, I expect to have 3, and then 2, and then 1, and then no x. But there is a missing term here for power of 2. So don't forget to leave a 0 for that missing term. Bring down the first term. 3 times 2 is 6. Negative 2 plus 6 is 4. 4 times 2 is 8. 0 plus 8 is 8. 8 times 2 is 16. 16 plus 16 times 2. 5 plus 16 is 21. 21 times 2, which is 42. And 42 minus 2 is 40. And you know this is the remainder. And you see that we got the same answer. So remainder theorem tells me instead of dividing and find the remainder, you can just plug into the function, and whatever you get, that's the remainder of that division. And you know, every time the remainder is 0, we can say that x minus 2 is a factor of that polynomial. And if remainder is not 0, like this example, so x minus 2 is not a factor. We can say x minus 2 is not a factor, or 2 is not a 0 of that. So the reason that we find factors is that from each factor we can find a 0. If x minus 2 is not a factor, so x equal 2 is not a 0 as well. The factor theorem is another theorem that tells us if k is a 0 of the polynomial f of x, then x minus k is also a factor. That's exactly what I said right now. We said here, we say x minus 2 in example 1 is not a factor, so it means x equal 2 is not a 0. If x minus 2 is a factor, we can say x equal 2 is also a 0. And how do we know if it's a factor or if it's a 0? Just by finding a remainder. If you use remainder theorem and find a remainder, if remainder is 0, you can claim, so yes, this is a factor, or yes, this is a 0. Now, it says determine if x minus 1 is a factor of this polynomial. And don't forget that our goal in this section or in this video is just finding the factors and the zeros of polynomials. So we learn about all of these theorems to help us find the factors of polynomials or find the zeros of polynomials. We want to know if x minus 1 is a factor of that polynomial. How do we know? How do we know if x minus 1 is a factor? Two different methods. I can use synthetic division and divide, see what do we get for remainder. Or I can use remainder theorem and, you know, if x equal to 1, so replace the x by 1 into the function. If I replace x by 1, let's see what do we get. First find the power. So 1 to the third power, which is 1. 1 times 2 is 2. First find the power. 1 squared is 1. 1 times 9 is 9. 13 times 1 is 13. And then bring down negative 6. 2 minus 9, which is negative 7. Negative 7 plus 13, which is 6. 6 minus 6 is 0. Okay, the remainder is 0. And you know that this number is the remainder. So the remainder is a 0. When remainder is 0, that means x minus 1 is a factor. Or you can say 1, x equal 1 is a 0 of that polynomial. You can also use synthetic division, like the one that I did in example 1, and then find the remainder from a synthetic division. Both of them works. And you know that every time we can find a factor of the polynomial, by dividing those together, we can find other factors. So right now, I'm not able to factor this polynomial by grouping them. But if I know that x minus 1 is one of the factors, and I start dividing f of x by x minus 1, the quotient of that division gives me the other factors of the polynomial. So let me do the synthetic division right now. I put 1 into the box, 2, -9, 13, and -6. And then bring down 2, 2 times 1, -7 times 1, 6 times 1, and then 0. And these 3 gives me the quotient. No x, 1x, 2x. So the quotient is 2x squared minus 7x plus 6, which means this is another factor of that polynomial. And you can see that how these two theorems can help me to find the factors of that polynomial when I'm not able to factor by grouping. And if I set them equal to 0, since this is a quadratic equation, I can use quadratic formula and then find all of the zeros of that polynomial. Let's look at another example. It says, use the factor theorem to find all zeros for the given polynomial with one of the known factors. So I know that x minus 1 is one of the factors of this. If x minus 1 is one of the factors, I can use, and then by the synthetic division, find the other factor. I did the synthetic division over here, and I found that 2x squared minus 7x plus 6 is another factor. So these two are the factors of f of x. Okay, but you want to find all of the real zeros. For zeros, you need to set them equal to 0 and find the zeros. Based on the zero product property, we set each of the parentheses separately equal to 0. And if I set 2x squared minus 7x plus 6 equal to 0, if you're not able to factor it, that's fine. You can just use quadratic formula. But let's try the AC method, see if you can use AC method. So A times C, so you know in this equation, A is 2, B is -7, and C is 6. A times C is 12, B is -7, and I'm looking for two numbers that if I multiply them together is 12, and add or subtraction is 7. And those numbers are -3 and -4. So what do we do in this case? Since A is not equal to 1, I cannot quickly open two parentheses. I have to break down the middle term. So I will keep the first term and the last term, but instead of -7x, I put -4x minus 3x. And then I have four terms. I put them in groups of 2. Try factoring the greatest common factor from each group. From the first group, 2 is a common factor, x is also a common factor. If I factor 2x and divide each of them by 2x, it gives me x minus 2. From the second group, 3 is a common factor, but I will factor -3 instead of +3 because I want the inside the parenthesis between the terms be a negative. And if I divide both by -3, it gives me x minus 2 again. And you see, we have the same parenthesis. Every time you use factor by grouping, you expect to receive the same parenthesis. Now you can write the parenthesis once, which is a common factor, and the remaining factors in another parenthesis. And if you set it equal to 0, based on the zero product property, you can set each parenthesis separately equal to 0. So x is equal to 3/2. And these are all of the factors, 1, 2, 3/2. These are all of the zeros of this polynomial. How did I find them when I wasn't able to factor by grouping first? I used remainder theorem, I used factor theorem to find all of the factors. Okay, but we can only use remainder theorem and factor theorem if we know one of the factors. One of the factors is known for us, or one of the zeros is known for us. If it's not, if we don't have any factors known for us, we have to start replacing different numbers to see which one gives us a zero as a remainder. But that may take a long time because there are infinitely many numbers that we can plug in for the x and see if we get the zero as a remainder. So guess and check, it's one way to find the factor, one of the zeros or one of the factors, but it's not very practical. That's the reason that we learn about the rational zero theorem, because the rational zero theorem gives us all possible zeros. And it narrowed down the number of possible zeros. Instead of guess and check infinitely many number, I only check those numbers that I get after using a rational zero theorem. How does the rational zero theorem work? So for rational zero theorem, I need to find two values, P and Q. P are all the factors of the constant term. Q, all the factors of the leading coefficient. I only need the constant term and the leading coefficient, and find all of the factors of each of them. Then I need to divide all P's by all Q's. And those numbers that I get, and don't forget that I need a plus and minus for each of them, okay? Because both of the positive and negative candidate may work. And then I will use those numbers for just replacing into the function and see if the remainder is zero or not infinity. So in this case, after using a rational zero theorem, we have just some limited number, not infinitely many number anymore. Let's look at this example. We have a polynomial. We don't know how to factor it. So I want to find one of the zeros and then divide by that to get the other zeros. But I have no idea what that first zero or what that first factor can be. So I'm going to use rational zero theorem. Based on rational zero theorem, I need to find two values, P and Q. P are the factors of the constant term. Q, factors of leading term. So what are all the factors of 4? All the numbers that you can divide 4 by. 1, 2, and 4. What are all the factors of 2 for Q? Just 1 and 2. Now I need to divide each P by each Q with a plus and minus, with the positive and negatives. So let's divide all of the P by 1. So 1 over 1, 1, 2 over 1, and 4 over 1. Now I'm going to divide them by 2, which is the second factor of Q. So 1 over 2, 2 over 2, and 4 over 2. Now I just simplify them and remove all of the repeating numbers. 1 over 1 is just 1. 2 over 1, which is 2. 4 over 1 is 4. 1 half. 2 over 2 is 1, so it's repeating. I'm not going to write it again. And 4 over 2 is also 2, which is repeating. So we are done. These are all possible rational zeros. These are all of the possible zeros of this polynomial. So if you want to know, but not all of them are the zeros. Okay, to make sure which one is the actual zero, you need to plug in this number based on the remainder theorem. You need to plug in each of these numbers for x and see which one gives you a zero as a remainder. Or you can use synthetic division to find and see which one gives you a remainder of zero. But when you use rational zero theorem, you are narrowing down all infinitely many numbers. You don't need to plug in all real numbers. You just need to plug in these numbers. That's it. Because these are only possible values that can be replaced for x. Now, when you see in part B, it says determine which of the possible rational zeros are zeros of the polynomial. So what do? We replace all these numbers for x based on the remainder theorem and see which one gives me a zero. If I replace all x's by 1, so don't forget to find the power first. 2 times 1 is 2. 1 to the third power is 1. Negative 5 times 1. 1 square is 1. Okay. 2 minus 5 is negative 3. Negative 3 plus 1 is negative 2. Negative 2 plus 4 is 2. Okay. The remainder is 2, is not 0. That means 1 is not a 0 of this polynomial. So 1 is not a 0. Now let's replace negative 1 for all of the x's. Negative 1 to the fourth power is positive 1. Positive 1 times 2 is 2. Negative 1 to the third power is negative 1. Negative 5 times negative 1 is positive 5. Negative 1 square is positive 1. Now if I add or subtract, 2 plus 5 is 7, plus 1 is 8, 8 plus 4 is 12. It's not 1. So negative 1 is also not a 0. You can use remainder theorem and plug in the numbers, or you can use synthetic division. But for synthetic division, you need to put these numbers in the box and then bring down all of the coefficients. Don't forget, if there is any missing term, replace it with 0, and then use synthetic division. Oh, you see, I got a 0 as a remainder for 2. So now I can say, yes, 2 is a 0. It's one of the zeros. Now you can do the same for negative 2. You can do the same for positive 4, for negative 4, for positive 1/2, for negative 1/2. You can either replace those numbers for x to see if it gives you a 0, or you can use it for synthetic division. So I don't have enough space here, but let's see. But you can finish this one later and find all of the zeros. But remember that you're only going to use these values. I tested positive and negative 1. None of them was a 0. I found 2 is a 0. We can find for negative 2 as well. So if I try negative 2 and use synthetic division, so it's 80, so it's not a 0. So negative 2 is also not a 0. I can try for 4. I can use synthetic division, or I can replace all of the x's by 4 for negative 4, positive 1/2, and negative 1/2. And since this is the fourth degree polynomial, you have at most 4 zeros. You found one of them, so you may be able to find the other three as well. From +4, -4, +1/2, and -1. And the last theorem that we learned in this part is called the fundamental theorem of algebra. So far, the other three theorem tells me that how I can find the factors of polynomial. I can use the rational zero theorem to find all of the possible rational zeros, then plug in each of them to see, based on the remainder theorem, which one gives me a remainder of 0, or use synthetic division to see if I get the remainder of 0, and if any one of those value gives me a remainder of 0, I say, okay, this is a factor. And I can find all of the zeros and all of the factors based on those theorems. But the fundamental theorem of algebra says that if we have a polynomial with degree n can be any positive number, that polynomial has at least one complex zero, imaginary zero. Okay, so every polynomial function can have at least one imaginary zero. And you can write all of those zeros in a parentheses. If these are, if C1, C2, and all of those to Cn are complex numbers, are the zeros, you can put each of them in a separate parentheses. Okay? Let's look at next example. So we're going to use all of these values to find the zeros of each polynomial function. Okay, I have a polynomial function here, and I'm not able to use the factor by grouping to factor it and find the zeros. So what do? First, it asks me to list all possible rational zeros. That means use the rational zero theorem. Rational zero theorem means find P and Q, find all factors of P and Q, divide them by each other. P is always the constant term, coming from the constant term, Q from the leading coefficient. All of the factors of 6 are 1, 2, 3, and 6. All of the factors of 1 are just 1. Then I need to divide each P by each Q. 1 over 1 with a plus and minus. 2 over 1, 3 over 1, and 6 over 1. So I have plus or minus 1. I have plus or minus 2, plus or minus 3, plus or minus 6. These are all possible rational zeros, possible zeros of this polynomial. That means if you are able to solve this one and find the zeros, you will see that the 3 zeros that you get is one of these numbers. Now it's asking me, now these are possible zeros. Now in part B asking me, now you find which one is actual zero. How do? Use remainder theorem, plugging these into the function, or use synthetic division. So I think that the synthetic division is easier and the chance of making mistake is less. So let's do synthetic division. So I need this polynomial, the coefficient of this polynomial for my synthetic division. And there is no missing term, so I put the coefficient 1, -2, -5, and 6. And I need to divide each time. I have to divide by one of those numbers on the list. I can divide it by 1. Then I will divide it by -1. Then I'm going to divide them by +2. Then divide them by -2. Then I can divide it by +3. I can also divide it by -3. Make a space here. And divide by +6 and -6. So let me do these numbers first and see if we get all of the zeros or not. Okay, for 1, I will bring down the first term. 1 times 1, -1, -1 times 1, -5 minus 1 is -6, -6 times 1 is -6. Oh, I got the first zero. So 1 is one of the zeros. So let me just put them in the box. Let's do another one. Divide by -1. Okay, the remainder is not a zero. Remainder is not a zero. Okay, got a zero. That's my second zero, second rational zero. Oh, next one. That's my next one. And since I had a third degree polynomial, since the degree was 3, I can have at most 3 zeros. And I found all 3 zeros, so I don't need to check the rest. So I'm done. I don't even need to check -3, check +6 or -6. So my answers are x equal 1, x equal -2, and x equal 3. These are the possible zeros. These are the zeros of this polynomial. Next example. We have a function, and we want to find all of the zeros. First, we need to list all possible rational zeros using P and Q. P are the constant term, the factors of constant term, and Q, the factors of leading coefficient. All of the possible factors of 17 are just 1 and 17 because there is no other number that you can divide 17 by. For 2, we have 1 and 2. So plus or minus P over Q, which means plus or minus 1 over 1, 1 over 2. 17 over 1, 17 over 2. So simplify a little. And these are all possible rational zeros. These are possible values, but not all of them are the zeros. Now, how do we find all the zeros? Using synthetic division. So for this polynomial, that's a degree 3. No term is missing. So I can use synthetic division and divide each time by one of these possible values. Divide by -1. Divide by +1/2. -1/2. Divide by 17. -17. Okay, let's finish these first. And if we couldn't find all 3 zeros by these divisions, we try the last numbers. So for 1, bring down 2. 2 times 1, negative 1, negative 1. 32 minus 1, 31 times 1. And if you add these together, so the remainder is not a 0. Not a 0. 2 times 1 half means 2 times 1 half means 2 over 2, which is 1. Negative 3 plus 1 is negative 2. Negative 2 times 1 half. So negative 2 times 1 half, you can cancel 2 by 2, so it gives you negative 1. 32 minus 1 is 31. 31 times 1 half, which is 31 over 2. Okay, I don't know what is 17 plus 31 over 2 right now, because I need to write them and find the common denominator. But something that's obvious is not a 0. Okay, so that I don't need to know the exact number. As long as it's not a 0, I know that 1 half is not a 0 of these polynomials. Let's divide by negative 1 half. Bring down 2. 2 times negative 1 half is negative 1. Negative 3 minus 1 is negative 4. Negative 4 times negative 1 half is positive 2. 32 plus 2 is 34. 34 times negative 1 half. So 34 times negative 1 half. You can simplify 2 by 34, so you get negative 17. And oh, that's my first 0. That's one of my zeros. Bring down 2. 2 times 17. 34 minus 3 is 31. 31 times 17, which is 527, plus 32, 559. 559 times 17 again is 9,503. So for sure it's not a 0 if you add them together. 2 times negative 17 is negative 34. Negative 37 times negative 17, which is 629, plus 32, 661. And if you multiply 661 by negative 17, you get negative 11,237, and for sure it's not a 0. So my only possible value that's left is 17 over 2 and negative 17 over 2. So I'm going to erase these numbers here to try for 17 over 2. Okay. So if I put 17 over 2 and negative 17 over 2, let's see what do we get. Bring down 2. 2 times 17 over 2, which is 17. 17 minus 3 is 14. 14 times 17 over 2. So 14 times 17 over 2. You can simplify 2 by 14, and you get only 17 times 7 is 119. 119 times 17 over 2. There is no way that you can simplify 2 by 119. You just need to multiply 119 by 17 and divide it by 2. Oh, I forgot to add these together. 119 plus 32 first. Oh, sorry. 119 plus 32, which is 151. Now 151 times 17 over 2, which is 250, 2,567 divided by 2. This is 1,283.5, and for sure, adding these two numbers doesn't give me a 0. And let's do the last number here. Bring down 2. 2 times negative 17 over 2, which is negative 17. Negative 17 minus 3 is negative 20. Negative 20 times, let me do it over here. Negative 20 times negative 17 over 2. If I simplify 2 and 20, I will have only negative 10 times negative 17, which is positive 170. 170 times plus 32 is 170 plus 32, which is 202. Then multiply 202 by negative 17 over 2. You can simplify 2 and 202. Then multiply 101 by 17. So it gives you negative 1,717. And if you add or subtract, you get negative 1,000. So for sure it's not a 0. So this is not also a root. So you see that out of all of these possible rational zeros, I only get one real 0. What does it mean? Based on the fundamental theorem of algebra, every polynomial function have at least one complex 0. So right now, I had a third degree polynomial here. I expected to have 3 zeros, but I only got 1 zero, which means the 2 other zeros are complex numbers. So I only have one real 0, which is negative 1/2, and the 2 other zeros that I expect to have are complex numbers. And if you want to find those complex numbers, you can let's see if I can find some space here. You can divide by the given 0 and then find the quotient to find other zeros. Now, you know that one of the zeros is negative 1/2. So you can start dividing this polynomial by negative 1/2. Okay, and you did it. That's over here. So this quotient, which is 2x squared minus 4x plus 34, that's a factor of that polynomial. You can set it equal to 0. Since this is a quadratic equation, you can use quadratic formula, okay, and find the complex zeros. So in this equation, A is 2, B is negative 4, and C is 34. Just plug in the number for ABC. Negative times a negative is positive 4, plus or minus. So let's see what's inside the radical. Inside the radical, I need to find the power. Negative 4 squared, which is negative 4 times negative 4 is positive 16. I need to multiply these three numbers. 4 times 2, which is 8, and 8 times 34 is 272, and 16 minus 272 is negative 256. And you can easily see that when under the radical we have a negative number, that means the answers are imaginary or complex number. So negative 256 means negative 1 times 256. Negative 1 means I, and 256, if you simplify 256, 256 is, let me see. See if we can find it. Yeah, it's 2 to the 8th power. So if I multiply 2 8 times, I will get 256. So it's actually, instead of 256, I can put 2 to the 2nd power times 2 to the 2nd power, 2 to the 2nd power times 2 to the 2nd power. And each of these powers will be cancelled by the radical. So 1, 2, 1, 1, 1, 4 2's will be out. Or we can say the square root of 256 is 16. So the answer is 16i. Since all of them are divisible by 4, I can divide each by 4 as well. And my final answers are 1 plus or minus 4i. I have two separate imaginary numbers, 1 plus 4i and 1 minus 4i. And you can see that this polynomial has two imaginary or two complex zeros. One real zero, negative 1/2, two complex zero.